All right, guys, I'd just like to go through the 3 examples that you were given. And I'd like to also go over one-sided limits. And this should help you with your worksheet. All right, so this first limit here. Remember, with every limit, when you start at, the first thing you should try and do is actually do some direct substitution. So this limit reads, the limit as x approaches 2. So what I can do in the beginning is I can try and substitute a 2 everywhere I see an x. So I do that. In the numerator, I've got 2 minus 2, that gives me 0. In the bottom, I've got 2 cubed, which is 8 minus 8, gives me 0 as well. Remember, 0 over 0 is what we call an indeterminate limit. Okay? Another indeterminate form is infinity over infinity, but in this case, we're talking 0 over 0. Now, in order to get rid of that indeterminate limit, or to correct that indeterminate limit, we actually have to reorganize the limit as we see it here, this x minus 2 over x cubed minus 8. Something weird's happening here that's causing that to equal 0 over 0. Now, in order to get rid of that indeterminate form, we have to do one of the following, right? And these are skills that you have developed over the course of your high school career, but we actually just practiced factoring not long ago. So factoring is an important topic. Rationalizing, all right, if you see radicals involved, chances are you may have to rationalize. Expanding, okay, expanding and simplifying. Or if you have a complex fraction, this option down here a lot of times works best, finding a common denominator, or multiplying everything by a common denominator. So we'll look at this one and see what we can do. What can we do to get rid of the indeterminate form? Well, it turns out like the numerator is as simple as it's going to get, but the denominator, all right, that is the difference of cubes. So when I go to factor the denominator, this is what it should look like. Remember to always write your limit notation. So it equals the limit as x approaches 2. I'm not doing anything to the numerator. The denominator factors x cubed minus 8. In the first bracket, you have the cubed root of x cubed, which would be x, minus the cubed root of 8, which would be 2. All right, in the next bracket, we have this first term squared. So x multiplied by itself gives me x squared. The second term is the product of these two. X times 2 gives me 2x, but it's the opposite sign. Okay, so if we see x times 2, we get that negative there. A lot of times, common mistake would be to write a negative 2x here. But you have to use the opposite sign with the difference of cubes. And the last term would be this 2 squared, so plus 4. Okay. Now, as I said earlier, what we wanted to do was try and reorganize this initial limit so that we could find a factor in the numerator that would cancel away. All right, and I have that situation here. X minus 2 in the numerator, x minus 2 in the denominator, they divide away. That just leaves you with a 1. Okay, now I can go back to my direct substitution. At this point, when I've gotten rid of the factor from the numerator and denominator, I can go back to substituting a 2 everywhere there's an x that remains. And when I go to this direct substitution, it's here where I can drop this limit notation. I no longer need to write the limit as x approaches 2. So I'd be left with a 1 in the numerator. In the denominator, 2 squared, that's a 4, plus 2 times 2, that's another 4. And we have this 4 back here. It's going to give us a final answer of 1 over 12. That is the intended height of the function. All right, our next example. Right, once again, we start with direct substitution. If I fill a 7 in for x, 7 plus 2 is 9. The square root of 9 is 3. 3 minus 3 gives me a 0. Okay. 7 in for x on the bottom gives me 7 minus 7, also 0 on the bottom. So once again, that is an indeterminate limit. All right. And if I look at my options for solving an indeterminate limit, I could factor, rationalize, expand, multiply by a common denominator. In this case, rationalizing is going to work best. Now, in order to rationalize this, we have to remember to multiply by the conjugate of radical x plus 2 minus 3. And the conjugate is simply radical x plus 2 plus 3. Now keep this in mind. If I multiply the numerator by radical x plus 2 plus 3, I also have to do the same to the denominator. Okay? Essentially multiplying the top and the bottom by root x plus 2 plus 3, that's essentially multiplying by root x plus 2 plus 3 divided by root x plus 2 plus 3. It's like saying you're multiplying by 1, which is perfectly okay. Multiplying by 1 would not change this. However, when we go to do this, it's going to simplify my limit. And hopefully, we'll end up with a factor in the numerator and the denominator that I can cancel. Now remember, shortcut for multiplying conjugates. First times first, radical x plus 2 times radical x plus 2 leaves me with x plus 2. Now I could multiply, if I did this times this, that would give me a positive 3 radical x plus 2, and then this times this, that would give me a minus 3 radical x plus 2. Those two terms will cancel one another. They'll sum to give me a 0, so I don't even need to do those, all right? I'm not going to show that. But it would be perfectly okay for you to do that, okay? I'm just going to go with first term times first term to give me x plus 2, and then last term times last to give me a minus 9. Keep in mind it's a minus. It will always be a minus because if this is a positive, that would be a negative. If this is a negative, that's a positive. Okay? I'm left with x plus 2 minus 9. Now on the bottom, I'm not going to expand that. I often get the question, well, why didn't you multiply that together if you did that to the numerator? Well, remember, the goal was to try and get a factor to cancel from the numerator and denominator. So I want to leave this x minus 7 away because I can see that when I simplify the numerator, x plus 2 minus 9, I get an x minus 7, which is good news because that factor, x minus 7, is the guy that's causing the problems. He's causing this original limit to equal 0 over 0. So when I divide these away, leaves a 1 up top, a 1 here. This is where I can go to back to direct substitution. So everywhere there's a 7 remaining, sorry, an x remaining, I'm going to fill in a 7. Okay, there's only an x down here. Don't forget, the numerator is now a 1. The denominator would become 7 plus 2, 9. The square root of 9 is 3 plus 3. That would give me a final answer of 1/6. That limit is equal to 1/6. Next one, okay? I'm going to show you how to do this one by factoring using the difference of squares. And I'll flip the page and you'll see another example. I'll pause the video for a minute so that you can pause the video and see how to do it by expanding. All right, I find this one easiest using the difference of squares. Don't forget, excuse me, don't forget that you should always try direct substitution first. If you fill a 0 in for h, a plus 0 is a squared is a squared. Minus a squared would give you a 0 up top. This h is approaching 0, means that would be a 0 down low. So I end up with an indeterminate limit. Now, in order to factor, a lot of people may not notice what type of factoring it is, but in fact what we have here is a perfect square minus another perfect square. So I can actually use the difference of squares to factor the numerator. Okay, what that would become, I would take the square root of this term and the square root of this term, put them in brackets, and then put opposite signs between them. So we'll start with a plus h squared. The square root of that is just a plus h. It would go to the front of each bracket. Let me get my bracket set up here for you. Then I'll take the square root of a squared. Well, the square root of a squared would just be a. it would go to the back of each bracket. Don't forget, with the difference of squares, you need a plus and a minus between them. Okay? Now, when I simplify those brackets, I'm left with, you got to ask yourself, what's a plus h plus a? Group your like terms. A plus a would give me 2a plus h. In this next bracket, a plus h minus a. Group your like terms again. A minus a, there's 0 a's left. There's only an h there. Now, this says the limit as h approaches 0 of 2a plus h times h divided by h. Well, you may notice that I have an h in the numerator and the denominator that I can divide away. Once I divide the factors away, I go back to direct substitution. So anywhere there is an h remaining, I fill in a 0. This would end up being 2a plus 0, which is 2a. The limit is equal to 2a. Now, I said I'm going to show you another method to do this. You can just pause, I'll scroll over to it. You can pause the screen and have a look at it. I'm not going to go all the way through it. But here it is here. If I go full screen, you can see that this same question was done by expanding. All right? And I ended up with the same answer, 2a. So if you'd like to pause the video here, that's great. All right, next thing I want to go over, there's also some extra examples from a previous worksheet. I'll scroll over those. You can pause the screen if you'd like to look at those other examples. And lastly, I want to talk about one-sided limits. Okay, one-sided limits. All right, we are looking at this piecewise function here. And I just noticed, okay, we're going to look at some one-sided limits. So we have this piecewise function, all right? And here's what I would suggest to you. Anytime you see this limit notation, all of these questions, 1, 2, 3, 4, 5, 6, say the word limit in them, all right? I would suggest using a little straight edge. Okay, what I mean by that is this first question, the limit as x approaches 2. We'll worry about this negative sign in a second. First, we got to figure out where x equals 2. All right, well, x equals 2 if I move 1, 2 blocks to the right. All right, I'm going to put up a little straight edge. Now, the negative sign, as it says, it indicates that we're approaching 2 from the left-hand side. So that's why the straight edge is good. It actually breaks your graph into left and right sides. Okay, now if I'm approaching from the left, I want to start on the left-hand side. So follow my cursor. What happens is I'm going to move towards an x value of 2, and when I hit the fence, stop, and just read the y value. Okay, so what's the y value right here? Well, the y value would be a height of 3. So as I approach 2 from the left, I'm arriving at a height of 3. So the answer to this question should be 3. Same thing, the limit as x approaches 2, only this time it's got a positive sign after the 2. I don't have to move the straight edge or this line here. Okay, it's staying at an x value of 2, only this time I'm approaching from the right-hand side. So that's this piece of the curve. And I'm going to slide along towards an x value of 2. Boom, I hit the curve. What's the height I arrive at? The height I arrive at is 1 unit up. Now, this should say 1. Perfect. Now, if it doesn't indicate what side you're approaching from, you actually have to check both the left-hand side and the right-hand side. All right? Now, how it works is, in order for a limit to exist, the limit from the left-hand side has to equal the limit from the right-hand side. Okay? You can see the limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right. I arrived at 2 different heights. The left-hand limit was 3, the right-hand limit was 1. That would indicate that the limit as x approaches 2 does not exist. Okay? Even though there was a left-hand limit and a right-hand limit, they were 2 different things. In order for this limit to exist, these 2 numbers would either both have to be 3, or they'd both have to be 1, or they'd both have to be equal. All right. Next up, I want to approach 5 from the left, the right, and then I'm going to check again. All right. So what I would do in this case is I would move my straight edge. When I approach 5 from the left, that's this side of the curve, okay, I arrive at a height of 2. Okay. When I approach 5 from the right, again, I arrive at the height of 2. So what does that mean? Both of these answers down here, the left-hand limit we saw was 2. The right-hand limit we saw was 2. That means the limit as x approaches 5, since these are both the same value, the limit as x approaches 5 of g of x is also 2. Last question we're going to look at, g at 5. All right, notice this doesn't say anything about a limit. It's not it's not asking you for the function's intended height. It's asking you for the function's defined height. When you see that, you can throw your little straight edge away. What you're actually trying to do is figure out what the height of the function is when x equals 5. So if I go 5 units to the right, I've got a choice. I've got this dot kind of floating in midair at about around a height of 1.2, or I've got this open dot at a height of 2. All right. Now remember, g at 5 actually indicates the defined height. So I have to pick the closed dot. The defined height in this case would equal 1.2 approximately. Okay. I will leave this example here for you. If you want to give that a try. All right, there's some questions down at the bottom. You can give those. Look, limit, 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 limit. There's 5 limits and there's 2 defined heights. So keep in mind when you're doing the defined height, you have to pick the closed dot. Hope this helps, and we'll be in touch.